So it is an old subject, and I think torsion needs to be revisited. And I think this conference deserves at least one talk about this. So I'll speak about what's known as Einstein-Cartan, but also sometimes you hear names Siama and Kibble theory. And when you couple it to fermions in curved space-times, what the effects are, and there's been a lot of literature about this. However, some important points have been missed. In particular, you know, I'm an expert on baryogenesis, and so I know how fermions behave in curved space-times, and this is where my expertise comes in. And I will tell you a little bit more about it, and sort of my intention is here to tell you that things have not been done completely correctly. One should pay attention to helicity conservation if you are looking at cosmological spaces, and this is the topic of my talk today. And I'll try to convince you that quite generically, if you have torsion of Cartain-Einstein type, that one should get cosmological bounds rather than singularity. And I will do this in semiclassical approximation. And of course, this is not the whole story. There are various other quantum gravitational effects. The question is how reliable that approximation is. And then I'll conclude. So why should we modify gravity? Well, there is dark matter and dark energy sectors we don't understand. That's one motivation. But the other one is, of course, maybe we can learn something about black hole and cosmological singularities, where also it's widely believed that general relativity breaks down. And one possible way of doing that is to modify it in a rather conservative way, namely, if this is your Einstein's equation, somehow include torsion in it. And well, we know that curvature couples to mass, but another fundamental property of particles is spin. Why shouldn't curvature couple to spin? And the way of doing this is through torsion. And of course, the way this is represented is by a non-symmetric part of the connection. So, and of course, you can build such a connection on curved space-times, and the question what it does it. And when you parallel transport a vector around the point, the ordinary curvature, what it does, it actually changes the direction of your vector. What torsion does also, it changes the size of the vector a little bit. Yeah, I will tell you in a moment. Yeah, I will tell you in a moment. So some historical remarks. There's been various claims in literature, and maybe the most important for this audience is from 1973, a short paper in Nature by Trautmann, who I believe is Polish, right? Who, I don't know whether anybody knows him personally. Oh, it's your supervisor, okay? Great. So I'm in the right place, and the statement was made that spin and torsion may avert singularities. And so I'll try to substantiate those claims, which are very, very old. But also some other, I guess, Popławski recently wrote some papers on the same subject, and claiming also that not only that, but also that torsion can help us understanding the origin of matter, inflation, and dark energy. Matter, dark matter, visible matter, and dark energy is pretty much everything that is kind of mysterious in cosmology. So I think it does deserve some kind of discussion, how realistic that is. So the first statement I want to make is a sign of warning, namely in all literature, as far as I could find, what's been used is so-called Weissenhoff fluid approximation to the way how fermions couple to torsion. And so the way fermions couple to torsion is through, actually this should be pi here, it's basically decoupled to what's usually referred to as the spin density, which is, spin density can be written as, one way of writing this is, you have 3 gammas. But then you can actually express it in terms of epsilon tensor times times the axial vector density. And that's a fundamental identity that simply comes from the definition what we mean by this antisymmetric combination of gammas and what we mean by gamma 5. And so if you look at this, then you all will see that this kind of current density is present in the standard model, namely standard model currents violate parity, right? And that is, or chirality if you wish, and that is therefore a kind of a term that you find in the standard model, this kind of current. No, there is only chirality violation here. As far as I could, I don't think that CP is necessarily violated here. Sorry? No, I don't think so. Yeah, that's, so it's chirality violating current. That's, I mean, that was Nobel Prize, right? So. And, but this Weissenhoff fluid approximation is saying that you can actually represent this kind of current with the so-called spin fluid, which has this kind of indices, and then an additional constraint where when you contract it at full velocity, you actually get 0. This 0 should be here. And what I'll argue here is that this kind of approximation misses an essential point. Namely, the main contribution comes actually from the 0 component of the axial vector current, which is actually not described by this Weissenhoff fluid approximation. So the dominant contribution actually is completely missed. But if you actually look at even this, this is maybe the oldest almost complete review on torsion. Actually, they do say there that we do not have currently a proper microscopic description of fermionic fluids that includes spin. And in the meantime, spin densities, but in the meantime, I think this has changed. Now we understand how to do that. At least I do understand. So there's been some progress. And I'll try to tell you what we have done, actually, by understanding how to do it microscopically. Yeah, that's all that is, yeah. I'm not postulating. I'll show you, yeah. I mean, I'll show you what I postulate in a moment. But I'm still reviewing what's been claimed. So this initial statement that one can get rid of cosmological and black hole singularities. My verdict currently is that it is possible but not yet proved, so more studies needs to be done on that. There is a good hope, there is evidence that this is actually correct. But there's been various other statements that this kind of bounce is followed by a period of inflation. I think this is correct only when you add an additional scalar field. Which is not what's been considered in that paper, so I would say probably not true. Natural candidate for dark matter, there's been no reliable mechanism proposed that actually comes from there. I would also say this is probably, well, it's questionable. And also natural candidate for baryonic matter, probably not true because this current doesn't violate CP violation. Natural candidate for dark energy, well, what you actually get is this kind of contribution. And this kind of contribution, if it comes from QCD, you actually get about 10 minus 31 electron volt to power 4. Power 4 is missing here. And that's maybe a couple of orders of magnitudes too large for dark energy. However, if you take this chiral condensate into account, there is no reason why should I take that into account, so which is many orders of magnitude bigger. So actually, I do not understand why this condensate should be taken into account, but the true chiral condensate shouldn't, and therefore this statement is very doubtful to have any merit. So. Possibly, yeah. But okay. Okay. Well, does it come as a squared of axial current? With G in front? Well, no, there is no discussion. This is definitely there. But if you want to say that this is the dark energy, then why this is not? That's not explained. This is not a coherently oscillating field. Yes. If there is a chiral condensate, then there is no reason why it should scale. I mean, that's a statement. Look, if this oscillates, of course, doesn't behave at scale as dark energy. I completely agree with you. Well, no. Let me ask you the following question: the chiral condensate of QCD, does it oscillate?
No, because it doesn't have that form. Chiral condensate of QCD is psi 1 psi. Sorry, it's not psi bar gamma mu gamma phi psi. This is condensate which gives you preferred frame.
Yeah. No, it doesn't, because this one here is squared. No, it's squared. Okay, maybe I should not have put in here gamma 0, sorry. No, you're right. I should not put gamma 0 there. I made a mistake. Yeah, but just the usual chiral condensate. Right. Yeah, but here there is gamma mu squared. And then it's fully Lorentz covariant, and it doesn't have to oscillate. Yeah, sure. Yeah. Okay, yeah, you're right. I wrote it incorrectly. What I mean is the chiral condensate of QCD. Sorry, it's a typo. So. Yeah, in the Cartain-Einstein theory, the torsion is generated locally by coupling to fermion. I'll explain it in a moment. Not like that here. No, I'm just very conservative here. So as I said, the connection is replaced, in general contains the Levi-Civita plus something else, and this something else could have a non-symmetric part of the connection, and how do you get that? Well, you can introduce it simply in both in the Ricci and in the matter Lagrangian, and then if the matter Lagrangian depends on S, when you vary this with respect to S, you will get this kind of Cartan equation. So that's where the name comes from. And I will actually consider a theory where the source of torsion here comes from Lagrange multiplier, basically with fermionic current. And what you should notice here is that this equation is actually algebraic, so it doesn't appear as dynamical equation. So in principle, you can actually solve it. And that's indeed, I think, what's the most economical way of studying the theory, if you don't want to confuse yourself about what torsion means at every point in space. So the theory I'll consider here is the usual theory of fermions plus with masses plus this kind of coupling, right? And in principle, if you just require general covariance, you can actually couple the torsion tensor to the chiral current. You can also couple it to the vector current with different strengths. In the traditional Cartain-Einstein theory, this C is equal to 1 and C prime is equal to 0. And you, on mathematical grounds, you might argue that there is a good reason to put C equal to 1 and C prime equal to 0. But what I'll assume here, I'll assume no further symmetry but general relativity, so I'll assume that just as the usual Lagrange multipliers there and allow for the freedom to actually keep C and C prime arbitrary. And then you can actually, as I already pointed out, that this Lagrange, this Cartan equation actually is non-dynamical, so the torsion induced by this kind of coupling actually is local in space. Wherever you have a fermion, you have a local torsion, you can measure it. But torsion doesn't propagate, so you can actually integrate it out. And when you do, you actually get a full Fermi interaction whose strength is G times C squared. And C prime is here assumed to be 0 for simplicity, right? And this is just the usual full Fermi interaction. And now what we can actually do is you can just say that, forget about torsion, I integrated it out. Now I can deal with the theory as if it is just normal general relativity with additional contribution to the stress energy tensor that comes from this kind of interaction. And diagrammatically what I've done is, if you think of it as being a torsion that connects fermions, to which fermions couple, when you integrate it out, actually I replace this kind of interaction with that kind of interaction. Normally, you would say that to do that, you need a large mass in the propagator. If this is a propagating degree of freedom, but since torsion is not propagating, this actually procedure is completely legitimate even in the massless limit, right? So, and this doing that, actually you end up with the Cartain-Einstein Stiama-Kibble theory. And of course, this appears in two different ways. It appears that it corrects dynamics of fermions, and it also appears in such a way that it corrects dynamics of space-time. So if you are looking at cosmology, it does affect evolutional cosmology. Since this interaction is suppressed by G Newton, so it's dimension 6 operator, so it has to have a dimensionality -2 in front with the coupling constant. The coupling constant is naturally Newton's strength. It's a very weak interaction, and in our room here, we would not see it. But the only way that actually you might have a significant impact, just based on dimensional grounds, on the dynamics is actually close to singularities. And indeed, I'll convince you that this is actually the case. Very weak, actually. On this parameter here, actually, my best, when I looked at the one paper with the review on bounds, the way I could translate it, that this parameter C is less than about 10 to the 30. Yeah. Something very similar. Yeah, you see, the thing is, the sign here is determined because the coupling always comes squared. So you cannot. It will be also psi prime squared term, and it will be exactly the same term except that there is no gamma 5 here and no gamma 5 there. But it's a full Fermi interaction, which now is vector current squared rather than as axial vector current squared. So that's the only difference. And of course, you can actually assume that you start with, yes? Yes. Okay, and then gives you, okay, thanks. Then 10 to the 30. No, I said 10 to the 30. Yeah, I said in the measure, this, see, yeah, exactly. So when you, so it is like Planck scale divided 10 to the roughly 15, that's what I said. And that's precisely agrees with what you said. But you're right. Yeah, okay, you're right. Also, but I extracted this bound from low energy experiments, in fact, which I guess have, according to what you just said, it's a similar bound. Okay, sure. Yeah. Okay. So, so therefore, this does agree 10 to 30. Yeah. And so, of course, you can now, if you want to study what happens in expanding space-times, you can do various things. The simplest you can do, and this is what we did first, assume homogeneous state. And then we can solve this equation in some approximation, and I'll tell you how we do that. So homogeneous state means you assume the background being homogeneous and isotropic, that's the metric therefore, and also the state respect the same symmetry. You also know that fermions decouple conformally if they are massless, so you can just conformally rescale it. This is how the rescaling goes. And then the covariant derivative becomes ordinary. It's a well-known fact. So if you take that into account and go to momentum space, that equation becomes this one. So you see what actually happened here. This is now conformal rescale field. Maybe the most important thing to notice is the mass breaks conformal symmetry because of the scale factor here. And also this term here tends to scale away in an expanding universe, but in contracting universe, it tends to grow. And now what is next important is that to observe that helicity as an operator commutes with the fermionic Dirac operator in expanding space-time, so therefore it makes a lot of sense to actually write a fermion, break it into helicity plus and minus states, and in that case this gamma dot k becomes helicity operator times some gamma factors acting on psi h, and this is then the eigenstate of h hat acting on psi h, just give you h psi h. So this equation becomes simple of that form. For the actually there should be index h here that is missing. So now this equation is actually the left-hand side is diagonal in helicity space, so there is no breakdown of helicity, and my spinors are now two spinors, and here there's just some integral that generates something like a non-local mass or non-local. Generates some time-dependent mass or time-dependent some kind of field, gauge field, which is in condensed matter they call them virtual fields, but they actually act as fields. And of course, you have to calculate it. Now, the formalism to use here is to, if you want to evolve this in non-equilibrium setting, you should use Schwinger-Keldysh formalism. And for that, we need the Keldysh propagator, and this propagator actually, the Weizmann function is one component of that propagator, which is of relevance here. And so its definition is Wigner transform of the two-point function, if you want it in Wigner space. And then you can actually decompose it, and if helicity is conserved, the 4x4 Weizmann function breaks down into 2x2 sector. This sector is diagonal in helicity, but this sector here is the chirality sector, and of course this mass breaks chiralities, so I still have the 2x2 matrix. So I have four different densities characterizing the two-point function, and the physical meaning of these densities, you have actually vector density, just the density of particles basically. You also have a scalar density and pseudoscalar density, and you also have axial vector density. So these are the four densities that actually represent the on-shell version of this GH. And this is, so we can actually represent the fermionic equation for the mode function, if you promote it to the equation for the two-point function, you actually just get the evolution for these four densities. And so you get, and how it works in detail, so these are actually the equations for the scalar, pseudoscalar, and axial vector density. And this is the equation for the vector density. It's just not occurrence, so it's absolutely conserved, so you don't have to worry about it. But the axial vector density only couples to, there is no source coming from the term induced by the torsion. However, scalar and pseudoscalar do contain no local sources, and somehow you get integral differential equations for the density that you need to somehow solve. And fortunately, I had a good master student who actually did that. He solved those equations. And but before I do that, I should probably tell you something about renormalization. Of course, we are mostly interested in the infrared effects, but we also need to renormalize it. And the only reason why we haven't posted that paper yet is because we're still kind of discussing how to do that precisely. But to cut the story short, it turns out since fermions couple conformally, the only thing there is an anomaly, plus the mass term actually induces divergence that can be absorbed in the redefinition of the Newton constant. So Newton constant gets renormalized. I don't want to go much into this, but we have now control over that since basically last week. And what I'll discuss here now, I'll assume that divergences are subtracted, and I'll focus on the classical part of those equations. Namely, I'll assume that I have a thermal state, and the thermal state can be induced by some initial thermal state that is induced by is proportional. So this is the sum of the scalar and pseudoscalar density that is proportional to the real and imaginary mass. So this is the complex mass of the fermion. And then you have axial density that is proportional to helicity times the vector field. And then you have these integrated densities and moments of integrated densities. And then also what Stefano realized, that we can actually rewrite these integral differential equations that we actually get. We can actually rewrite it as the equation for generating functional of these objects here. And when you actually do that, these equations, the relevant equation becomes the equation for nu h, which is a combination of scalar and pseudoscalar density, actually generating functionals for those. So the equation becomes relatively simple. It still looks pretty horrible because, well, it's nonlinear, first of all. Nevertheless, so this parameter rho is actually the parameter that's introduced, which replaces sort of the moments of these moments here of the densities. So you introduce continuous parameter rho to actually define generating functional. And then basically what Stefano realized, that you can actually reduce that equation to an equation that solves, you can actually write the solution in this form, where this f actually satisfies the Volterra equation of the second kind. And that Volterra equation can be actually solved in certain limits. And this was the strategy actually that we use, which is, as far as I know, a completely novel strategy to solve this class of equations. And in fact, in certain limit, we can actually solve it for general scale factor, which is quite impressive. And so you see in the limit when temperature is small with respect to Hubble parameter, we can actually solve it analytically. And I'll just now show you the solutions. One solution is like this. If you fix the background, that means you assume that there is no quantum back reaction coming from fermionic currents at all, just fixed background, and you let it evolve classically. The stress energy tensor contribution, the normal fermionic contribution goes like this, so it's just some smooth curve. But if you take into account the contribution coming from torsion, then you realize that when the scale factor becomes smaller and smaller, there is a negative contribution to the energy density induced by the torsion. And this comes from particle creation, basically, that is there Now, in terms of this generic functional, this nu is a little bit like when rho is 0, it's the density of particles, basically. That's what you have, as density per unit volume. So the T00 is actually can be, this is the tree level part, and this is the part coming from torsion. And this alpha 5 is actually the coupling induced by torsion, which I should have told you what it is. It's actually, it's 3 pi g c square over 2, right? So it's one of a Planck scale kind of coupling. So what is maybe significant here is there is a zeroth order part which naturally scales 1 over 8 to the 4th. There is the torsion induced part which scales 1 over 8 to the 6th. It has two contributions. One of them is quadratic in the axial vector current, and one of them is quadratic in the scalar and pseudoscalar currents. And the question is which one dominates, and well, this one is suppressed by the mass. So when the mass is when you are in the non-relativistic regime, then the scalar and pseudoscalar contribution will dominate, but when you're in the relativistic regime, then the axial vector current dominates, which was completely neglected in the treatment so far. So close to the bounds, it's reasonable to assume that this term actually is by far the dominant term. And now this term here actually does scale as 1 over 8 to the 6th. Close to the close. So now what you see here, first of all, this sign is not negotiable. So it's a negative contribution to the energy density. And it does something very important. So negative contribution to energy density violates some energy conditions, right? Or positivity, for example. So if you look at this thing here I'm violating positivity of energy conditions, so which is usually assumed if you want to prove Penrose singularity, Penrose and Hawking singularity theorems. So this term here, if you let it evolve long enough, it definitely break those theorems. Yes, it is exactly what he claimed, but based upon very simplifying picture. Now this is a microscopic treatment, and I think it's also two-loop, formally at the loop level, because if you look at what we are doing here, we are, it's a full Fermi interaction that it's effectively two-loop diagram that we are calculating at the level of stress energy tensor. So none of this was actually taken into account in the former treatment. So what I should add maybe is there is also a conformal anomaly here that will also give you contribution 1 over 8 to the 6th. And there is another anomaly I didn't really mention, that it gives you 1 over 8 to the 4 log 8 term, which is subdominant when the universe contracts. Yes? Yes. Yes. Yes.
But I have a big problem with that, because you have a contact interaction for Fermi interaction. This interaction becomes strong about the coefficient inverse mass, whatever you do.
Okay, exactly. I'll discuss that. I'll discuss it. Okay, yeah. So of course, if you want a self-consistent treatment, you need to solve this equation self-consistently. So there is some background fluid, plus this fermionic fluid contribution, which consists of two parts, the one loop and two loop parts, if you wish. But the important contribution is, of course, coming from torsion, and we would like to understand this. In other words, the influence of that guy. And so if you start with the matter-dominated universe and then you let it collapse through, what you actually see is without torsion, you would just go to single point here. You would just go to singularity here. You would have a big crunch. Now with torsion, the evolution is the bounce, and this is actually I drew it by hand. I mean, you can actually convince yourself that the Ricci scale evolves from 0. It goes as 1 over t squared here, 1 over eta squared, or 1 over t squared here, and it reaches maximum at the bounds, and then again it goes 1 over t squared away from the bounds. So, so actually the bounds is the point of maximum Ricci curvature. And I think there is a fair conclusion here, which now we could discuss how reliable that conclusion is, that there is a bounce here. And similarly, if you in the radiation-dominated universe, you see the same. Now, these two curves, one of them is actually without including particle production, just classical back reaction, if you wish, coming from the fluid. And the other curve is the one when you include quantum back reaction and particle production. And that one, you see, gives you a slightly earlier bounce and delay in the expansion later. So there is some effect of particle production, but it's not that great. It's not that big. This is, of course, for certain set of parameters. You could change that, the amount of how this is influenced. Now, yeah, so this is now, I'll try to answer your question, some sort of dimensional analysis. So the structure of the equation is, roughly speaking, rho. And if you look at it a little bit carefully, this goes to rho to power 3/2. And if you assume that your rho close to the bounds goes to t to the 4th, which is, I believe, reasonable. This, by the way, also comes from the axial vector component, this kind of scaling. You actually get from here immediately that rho at the bounds is mp to the 4th divided by c to the 4th. Or Ricci scalar is mp squared over c to the 4th. So you see that if c is 1, you're completely right. I have a Planck scale bounce, and I cannot trust it. But I believe if I allow c to vary and be much greater than 1, then what I'm doing actually, the scale at which this term becomes relevant actually is below the Planck scale, and I can trust it. Now, I think I can. Sorry? Yes. Why does it have to be replaced by anything? I think it's the Planck scale, but let's discuss it. Exactly. I'm not using it as anything. I'm just. It violates unitarity at what scale here? At the Planck scale. Why does it violate unitarity? But at the Planck scale. My original theory is the theory that is fully. Yes. Okay, let's discuss it a bit more, but I have to finish my talk. So. Yeah. Okay. I was hoping that it's not controversial, but now I was wrong. Yeah, so it seems like it's fairly controversial. Yeah, which is I'm not sure that's a good or bad sign. Um, okay. No, well, I mean, what I did is I analyzed the divergences of the theories, subtracting them properly in dim reg. And then what I was left with is some initial thermal state that dominates the evolution. So it is classical in the end. But plus the quantum correction due to particle creation that is also included here.
Because your reference point is the Planck scale. You see, Planck scale is a quantum scale, unless you take your limit. So, Planck scale is a quantum scale, and then you can always measure relative to Planck scale.
Yeah, but
No matter how what it is,
but this is my Ricci. It's suppressed. It's not a Planck scale Ricci.
no, you're not getting the point.
I'm not. Yeah.
In the formal classical solution, your Ricci could be small. Question is whether I should trust your classical solution.
It's not a classical. It's two loop result.
I understand you integrate two,
It's semiclassical.
you integrate two loops, certain things, you plug it back, you solve for magic. Now whether it's classical.
Yes.
Question is, should I trust this or not?
Let's this.
I cannot trust it about the scales of the coefficient of this four-Fermi interaction. Period.
No. Let us discuss quantum gravitational correction in private. I'm okay.
Breakdown of the effective field. Four-Fermi interaction. Your effective field breaks down at the scale 1 over given by the scale.
You are saying higher loop corrections will be more important.
Four-Fermi scattering will become stronger than scale. Everything will go wrong. Come on, let's not reinvent textbooks things about effective field. We all agree that four-Fermi interaction breaks down.
Yeah. Yeah, but this is not. You see, this is not. There is no dynamical propagator. Okay. What are my conclusions? Is that I think one should consider seriously torsion, Cartain-Einstein torsion, as modification of gravity, and it should tell us something about singularity formation, at least for homogeneous collapse and for C much greater than 1. Of course, that's the controversial statement. And we have included quantum loop effects in our treatment, which is never done before. We also treated even classically, I think, for the first time correctly. And if you apply to black hole physics, helicity is not anymore conserved, so one has to do more sophisticated treatment to actually solve for fermions. Yeah. So I think that one should actually definitely revisit the Cartain-Einstein, the singularity theorems in Cartain-Einstein theory, which have not been well posed, as far as I know. Thank you.
Well, there's negative time for questions.
Yeah.
The problem is that you cannot have a coherent state because you cannot just pile fermion particles on top of a given state. You have Fermi's exclusion principle. So on the other hand, I mean, you could.
Well, these equations that I solve satisfy the Pauli exclusion principle. I'm not piling anything that is not permitted by the laws of quantum mechanics.
So yeah, so one way of bypassing this objection is actually just to have these things called classical spin.
No, that's okay. The objection is not. I don't want to be misunderstood because this is the most important point, most important controversy. So it's okay to that for example, QCD condensate, right, of quark. Perfectly fine. It's bilinear and it's bosonic. I can take QCD condensate data. No. I can take QCD condensate data, plug it into the equations, and then solve what's right. The problem is not this. Let's try to understand what is the problem they solve. Right? He's telling us he can take care of singularity. Now, what is normal perception of singularity? We all understand that singularity, if nothing happens before, at the Planck scale, we have to take into account very strong quantum gravity fluctuations and stuff like this. Right? Now, the solution of singularity problem would be if he manages he has a consistently bouncing universe, before you have to take into account quantum effects.
Before.
Right. Now the problem is that since his reference point is the ratio of the Planck mass to his scale, classicality is irrelevant. Because for any h bar, no matter how small he takes m Planck, this scale follows.
Okay, Guillaume.
Here will break down at that scale.
Okay, Gia. It's a very simple point here. So what you are saying, this is my theory. You see, I only have at the fundamental level, I only have this, two Fermi coupling to torsion. Now that induces torsion connection on my manifold, and the coupling strength is dimensionless parameter C here. Now you are saying that this relatively innocent dimensionless parameter is simply shifts my Planck scale from MP to MP over XC squared.
In Starobinsky inflation, for example, right? The component
I-
I can tell you formally, if I take phi square r, coefficient is dimensionless. And many people are making mistakes saying, oh, this is a dimensionless coefficient. But whether your interaction violates unitarity or not, you can only judge after you canonically normalize your field. Then dimensionless coefficient comes with entourage of the Planck scale. As you see it explicitly from your computation.
No, I disagree. Let me just make this as a comment. I wrote a paper where I proved what you've just said is incorrect. I wrote a paper about it. Read my paper. Look, I'll tell you what I wrote in that paper. We considered graviton scattering of this type, and we proved that this kind of scattering violates the unitarity. The Planck scale even exceeds much greater than 1 of the nominal coupling.
Do I have to trust your four-Fermi interaction or not?
Well, what I'm saying is, you see, your argument.
You give me four-Fermi interaction.
I'm saying that this does not necessarily reduce the Planck scale.
I have a question.
You have to prove it, or I would.
No, I don't have to prove it. What I'm saying is the reality textbook.
No.
Four-Fermi interaction, it breaks unitarity.
No, it's not. No.
No, I don't understand what you're saying.
We can fight over lunch.
Sorry, this is I cannot.
Well, there could be. You see, Gia, you are right. If there might be cancellations of naive diagrams that
Can I keep
contribute.
the microphone?